My name is Joe Chow. I'm from Rensselaer Polytechnic Institute. I work on Synchrophasor data for a long time, but not directly with Jim and with Arun, because I actually work with a lot of people that work with them. And they include David Bertinoli, Harish Mader, Jay Murphy, Nick Schultz, and Jim Ingleson, who retired from NEI. So, okay, thanks. Oh, last year we have a really pleasant trip to Inner Mongolia with at the invitation of Professor B, who will be actually speaking next. And I looked at the picture for a while. I said, well, wouldn't it be nice if you can put a GPS antenna right over there? You know, that's just 360-degree sky view, no interruption. So I mean, the hospitality from the Chinese is immense, and here we are sitting in something. Is that called yurk? Yurk. Okay, yeah. So it's a Mongolian tent. This is round, and we have a great time. So now I'm going to talk about synchrophasors for state estimation, and of course the original idea came from the 85, 86 paper with Arun, Jim, and Kamir. Kamir is now working in Boeing, okay, and
He designed streamlined power system.
Oh, okay.
Those batteries?
Yes.
I'll mention it again.
Now, of course, this is similar to the presentation I make at the North China Electric Power University. We have some improvement to that, but Arun talked to me after. He said, the state estimated solution is solved. It's a direct calculation. Why do you worry about this? But I'm really a stubborn guy, and I like to work in the muck. Okay, that we were trying to use synchrophasor data to do some calculations. I wasn't terribly happy with the data that we have. So now, in terms of state estimation, so the early approach is to put PMU data to the traditional scalar estimator, and I think NIPER had this implementation for a while. And more recently, an M.S.E.E project, I believe, is undertaken by TVA Energy and Osram, who did that exploratory work. And Professor Ali Abu also has shown the benefit of having PMU data to improve the convergence of the state estimated solution. And then, of course, with one of the DOE program, Dominion and Virginia Tech working on a three-phase tracking state estimating. What my interest is really related to all the other research I'm doing, is to actually look at a state estimator using synchrophasor data only. And the bottom line is basically build a state estimator running at 30 samples per second, higher if you have data coming in, using synchrophasor measurements, and it's really intended for high voltage buses. Now, why do you want to use this calculation? First of all, you can, if you don't have a phasor measurement unit, you can actually use you can generate these pseudo PMU measurements. And then when you have multiple PMUs in a network, you can start cross-validating those network. And most recently, you see our pool of problems are so enticing that computer scientists at University of Massachusetts and Amherst was doing PMU placement analysis using set theory, and they have some really interesting results. Enabling, for example, calculation of the interface flows. And in a lot of the systems, you cannot really put a PMU right at a generator, so you actually have to surround this bus with other PMUs so that you can actually calculate this. And for example, when this thing rolls out, we'll have actually some really good wind turbine performance data coming out, because in northern New York, because the way that we actually put the PMUs together. And then, of course, you can actually see disturbances as they come along, look at order stability, frequency response, and so on. And part of the slides you see is we actually make these presentations to New York ISO and ISO New England, so some of these things, baggages came along. What is needed for phased state estimator? Good coverage, okay? And it turns out that if you have 1/3 coverage, you have observability, and you have 1/2 coverage, you actually have cross validation. And this actually happens in New York and New England. Okay? So this is a great opportunity. And you don't actually need any network data. You actually don't need any low values, but you do need the network data. You can do a simple least square algorithm, but you want to be able to correct for like the scaling errors and phase biases. You don't need differential equations. Of course, if you want to go into the generator, then you actually have to run a dynamic state estimate. And then for real-time operation, you can launch from PDC. And one of the things that I would like to see is a cross-regional state estimator at the high voltage bus from all the way from MISO to PJM to New York to New England. I think that's really the legacy of Arun and Jim. So that's how we can do it. So we start, the reason why we do this, we start looking at this. This is the Macrodyne PMU system. We don't have any of the new SGIG PMU data to work with, so we use that system. And it is literally in the central New York. M.S.E.E is a critical bus, okay? And then the PMUs are located with this green diamond. And then we can actually look at all the buses in the central New York. This covers about half of the 1/3 of the New York system. Okay. And then so one of the things that we want to calculate is the fact that New York operates on, the operators will look at all the interfaces. There's about 7 or 8 of those all over the place. And what we would like to do is duplicate those calculations. And of course, we only have the 345, and soon we'll also have the 230. But we won't keep the 115, and that needs to be, that's for future considerations. So let me just, what is the difference between phased state estimation and regular scalar? So this is part of it, okay? So the blue trace that shows the implication of generation trip, you can actually see a nice voltage response, whereas a scalar, you just see a drop about 15 seconds later, okay, and you have no clue what's going on. The state estimation is run on a least square estimation, and the key part of it is the looking at what can you put into this pot and stir it up. Basically, this is what it is. And we found that we consistently were puzzled with these phase angle bias. That, and we think that there could be timing error in whatever internal calculations, or maybe the length of the instrument cable and so on. But one thing that we feel it is useful information to use is that if you see a phase bias in one channel of a PMU from a location, you actually can count on the fact that it will show up in all other channels, because they use the same timing signal, they use the same EFT calculations and same filter, and we can actually just go on, pick up the difference. And it simply is the fact that you introduce these additional angles that you can correct. Sorry. And oops, going too fast. Okay, so for example, here we have 2 PMUs and a substation, and they actually, in steady state, they show about 0.25 degrees, very small, but there is a 0.25 degrees difference, and we can actually accommodate for that. The other thing we found is that this is the issue with CTs and PTs. Now, voltage is a lot easier to analyze because you know that it's between 1.0 per unit plus or minus a few percent. Okay. Now, current can vary during the day, so it's very difficult to catch issues in current. So we actually, whenever we have a large current scaling error, we actually can correct for it. And the idea is to, very simple, putting in some scaling factors over here. And we look at a number of events. And the really good events to study are loss of generation, 700-800 megawatts, and you can actually see a good signature in the system. And these are the NIPER data, and of course, the information we got is from ELU's FNet system, and Dave will help us tell us, what's going on and so on. Okay. So these are the parameters that we can estimate. So we estimated the phase bias on 5 of the 6 PMUs. We have to set one of them to be a constant. And some current scaling error that we actually do that. Well, you can also now do a line parameter estimation. So we try this out, and these are some of the results. For example, the angle bias. They are small, okay? This is between like 0.2 degrees. Current error is in the two lines that we have, they actually was not really calibrated well. It's nothing to do with the PMU, but it's the calibration of the CTs. And one of them is consistently off by 7%. The other one is off by about 10%. And we actually can estimate the tab as well. So as a professor, I think these are really interesting plots. For example, here you actually have auto transformer switching taps. Okay? And the nice thing to illustrate is that, for example, when this tap goes up, the other tap changes too. And you know that the other tap didn't move. Okay? These are two parallel auto transformers. But you can see the nonlinearities in the system when you use a linear model to model the transformer reactance. So one of the things that in this Synchrophasor standard is looking at the accuracy. So there's this thing called a total vector error. Now for us, what we are looking at is that how do we actually look at the accuracy of the PNU data over network? There's no reference that we can use. So instead, what we did is that we took the phasor state estimator solution and use it as sort of the accurate value, the reference value, and compare the measurements to it. So now, of course, we actually have to put the current scaling in this calculation, otherwise the number doesn't look very good. So we did put the current scaling, but we in the first column, in the first column, the mean TBE is slightly over 1%. But there's no angle correction. If we start also correcting the angle bias, now they're all within 1%. Okay, and of course, the standard says you have to be less than 1%. So the system actually works well. Okay, and you can actually monitor the interface calculation as well. So for example, their direction flows disturbance. So if you have a disturbance to the east, all your east-west lines will see a difference in the flow, and the north-south line doesn't see a flow. Okay, all these things just tells the power system work just as expected. Okay, conclusions. I think I'd just like to point out the fact that we have been talking to the last bullet, we have been talking to New York and New England, try to really get them to take a look at this technology and slowly move from there to the other operating regions as well. Thank you.